Section 5.4, finding empirical probabilities. Okay, so empirical means they come from an experiment or an observation or an action. So we need to simulate an experiment sometimes because sometimes you don't have the tools or the time to actually do it. So a lot of ways that we're going to simulate experiments in this class are to use random number tables or random number generators. Okay, first we're going to use a random number table, which has been provided for us, to approximate the probability that a fair six-sided die will land with a 6 showing. We're going to do 10 trials. Okay, so how you use a random number table is basically you just move your way. You start at the beginning, move your way down it, and as you come to the numbers that make sense in your context, you use those numbers. And if it's a number that doesn't make sense in your context, you just skip it. So if we're rolling a 6-sided die, the only numbers that make sense to us are 1, 2, 3, 4, 5, and 6. And any other numbers I'm just going to skip. Okay, so I'm just going to start down my number table. The first number I hit is a number 4. So the first roll is a 4. Second roll is also a 4. Third roll is a 6. 8 doesn't make sense in my context, neither does 7. So I just skip all of those. Next roll is a 5. 0 doesn't make sense. Next roll is a 3, a 2, skip, a 3, a 4, skip, a 1, skip, and a 2. And that simulates my 10 trials, my 10 rolls. Now in this example, I was trying to see what the probability was of rolling a 6. That only happened one time out of the 10. So for us in this example, in this particular experiment, the probability of rolling a 6 out of 10 total times was just once. It was just a 10% chance. Again, these are empirical probabilities based on experiments, so it's okay if it comes out to something that doesn't feel like what you think it should be, because what you're probably thinking of is that 1/6 probability, which is the theoretical probability. Okay, let's do it again, and let's use a random number generator online. So what you can do is I literally just Googled random number generator, and one pops up for you. Here you can change what you want your numbers to be, so you don't have to do that like skip numbers that don't make sense thing. Okay, so what we can do here is we can just say, do this 10 times for me, and let's record the numbers that we get back. So I'm going to do this on the fly right as we go here. I'm going to generate some numbers. First number is a 3, a 2, a 5, a 1, a 4, a 3, a 5, a 6, a 4, and a 1. I'm going to flip back over to my table here, and I'm going to record those back to us. So it was 3, 2, 5, 1, 4, 3, 5, 6, 4, 1. It very strangely enough only happened once again. I could perform that same simulation over and over and over again. I would not always get 1/10. Sometimes I would get 2/10. Sometimes I would get 3/10, 4/10. It would vary back and forth. But that's how empirical probabilities work, is they change from experiment to experiment. What this leads us to is our law of large numbers. If your simulation is designed correctly, then the more trials you do, the closer that empirical probability should come to the true probability. As you approach infinitely many trials, the empirical probability and the theoretical probability should approach the same value. So my simulation is fine in this example that I was just doing, but what I only did was I only did it 10 times. It's a very small sample. If I would have done this 100 times or 1,000 times, then I should get closer and closer to that 1/6 probability that I'm expecting. That's what the law of large numbers says. So here is a graph that kind of demonstrates what the law of large numbers does. This one in particular is for flipping a coin and whether or not it lands on heads. So it says as the number of trials is small, the empirical probabilities change a lot. So up here, whenever the number of trials is small, look at the difference. So what it looks like here is that the first time they rolled, they got a heads. So after one roll, the probability of getting a heads was 100% because it happened once. Then the more times they did it, that probability kept dropping from there. And what it does is, notice as my trials approach infinity, as I get more and more trials, that number settles down to about what I expect it to be. It settles down to about a 50% chance. If your simulation doesn't eventually settle down to what you think it should be, to that theoretical value, then there's basically two explanations. One, either your theoretical value is incorrect, so what you have accepted as the true probability is not true, or your empirical value is just varying and you should just continue to do more trials. So it seems like 1,000 trials is a lot, but if you did 10,000 trials, it should be even better, and 100,000 should be even better. One kind of last note on all of this is that no single outcome is ever due, which means if you were to flip heads 8 times in a row, then you feel like tails is more likely to happen on that 9th flip. But after each flip, it's completely independent of each other. Heads is no more likely to happen on that 9th try